Hey guys, welcome back to my YouTube channel. Today I'm going to be explaining the oxymercuration and demercuration reaction. So basically it consists of two steps. The first step is your oxymercuration step, and you can kind of tell in the name that's when you're adding your mercury. It's HgOAc, and then your second step is the demercuration step, and that's where you use NaBH4 to turn your HgOAc into a hydrogen. And the reason NaBH4 is used is because it's a reducing agent, so it's a source of H plus ions, and it can be given to carbon to form CH bonds. To start off, I have this example here on the right, and I'll be going over the mechanism for this first one. I also have more example problems on the bottom. Oh, and also this type of addition in this reaction is anti-addition, and you'll see that later on as well. All right, so for this first example I have here, I'll be explaining the mechanism. So for this first step, we're adding our HgOAc to, which is our it's our oxymercuration step. So if you look here, right, so your double bond is going to go away. And if we assume this methyl is on a wedge, your HgOAc is going to actually form a three-membered ring, right? It's going to form a three-membered ring with your Hg. I'm not going to draw the OAc for now, but just know it's there. So this three-membered ring, it's basically very unstable. So it makes these two carbons that the ring is attached to. So there's this one carbon here, one carbon here. It makes them partially positive because of the mercury. And so we can assume that they are attracted to nucleophiles. And in this reaction, we usually use water as a nucleophile, which is a weak nucleophile. But you can also use other weak nucleophiles. So this is your first step where you're adding your mercury. The three-membered ring forms, and now we're going to attack with our weak nucleophile, which in this example it's water. Sorry, H2O. Right, so this is going to attack your more substituted carbon. And in this case, it's that top one right there. And when we do that, the three-membered ring will break, and so your Hg will end up over here, and your OH will form a bond there. However, like I said earlier, this is anti-addition, so our water will not be on a dash, it will actually be on a wedge. So we can just put the OH here, and then our previous methyl group that was there, we'll just change that to a dash. Okay. And you might be thinking, why is it not water? Why is it OH? It actually is water at first, but then another water molecule comes and deprotonates the H2O. And that occurs for every weak nucleophile. And so this is our step there. And then for this next step, which is the second step, it's demercuration. We're going to be using the NaBH4 that I talked about earlier. And what this NaBH4 is going to do, it's going to change our mercury into a hydrogen atom. So we're going to have the same product, right? But our mercury will be an H, right? So this would be our final product. And yeah, that would be our final product for that example right there. And then if we scroll down here, I have some more examples, and I'm going to involve the stereochemistry in these examples. So this first one, let's view it from the bottom. If you're looking at the double bond right there, we'll have those two methyl groups coming towards us, or going away from us. They're on dashes. And then this top one, we'll put it on a wedge. All right. So from here, we can add our first step, which is adding the mercury, and it'll form a three-membered ring. Oops. That is on a wedge. I mean, on a dash, by the way. Sorry. And our three-membered ring will form here, right? Our water will attack the more substituted carbon, which is on the left there. And remember, it's anti-addition. So if you remember back from Newman projections, the anti will also look like this, right? So you have your mercury here and you have your water here, but remember it's OH because we deprotonate with another water molecule. So this is actually the anti-configuration here. And you can see that because the angle between the mercury and the OH, if you were to view it first of all, let me draw the substitutes on this. So on the OH, we had the wedged methyl and a dash methyl. And on this, since the three-membered ring broke, we still have the dash methyl here. All right, so if I were to draw the Newman projection of this, you'd see that the OH and the HG are actually in a 180-degree angle with each other. And that angle is called the anti-angle, and it's the best because there's the least amount of steric hindrance between the two groups, right? So our dihedral angle is 180 degrees. This is the anti-configuration. And just for more clarification, I'll actually draw the Newman projection here, right? So we have our, and I'm going to be viewing this from here, right? So our OH will be going down. We have a methyl group going to the right, methyl CH3. And then we have a methyl going to the left. That's also CH3. Actually, this will, sorry. So it'll actually be C3H, same thing, but we're just attaching to the carbon. And then in the back of the molecule, we have our mercury going up, right? And then we have a CH3 going to the left, right? All right, and also we'll have an hydrogen going here. So, right, so if you see in the Newman projection, the dihedral angle between the OH and the HG is 180 degrees, and this is your anti-configuration. Now, remember, our second step is demercuration, so we're going to be using NaBH4, and that's just going to change the mercury into a hydrogen, and so our final product will end up looking something like this. So we have the hydrogen there, which was converted from the HG because of the NaBH4, and we have OH here still, and the same substitutes. All right, so that's our final answer there. So the second example, if we look here, I'm actually not using water as a nucleophile here. I'm using CH3OH. It's another weak nucleophile, but it's the same process. All right, so if I'm viewing the molecule from here, let's draw this here. I'll draw this down here. All right, I have a methyl going there on a dash. I have my ethyl going there on a wedge, both of them on a wedge, sorry. And then our dashed ethyl here. So that's our molecule there if we add the stereochemistry. And then our first step, like I said before, first step is HCOAC. All right, so first step, we're going to form the three-membered ring. All right, and so once again, like I said before, the mercury forming the three-membered ring, it's going to make those two carbons that it's attached to partially positive. And so those two carbons are attracted to nucleophiles. And yeah, so our nucleophile here is CH3OH. Okay, and it's going to attack the more substituted carbon, which in this case is on the right. So we're going to attack this on the right. And we need the anti-configuration. So our HG, well here our, oh wait, hold on one second. And we need deprotonate, so it's actually going to be OCH3. Okay, and then on the other side, we have our mercury because the three-membered ring broke. And with the OCH3, we have two substitutes that we need to include still. It's our wedged methyl, and we also have our dashed ethyl. And on the mercury, we have our wedged ethyl. All right, and if you see in this molecule, we do have the anti-configuration, which is very important. 180 degree, like I said before, less steric hindrance. And in our second step, we're going to use NaBH4, which will turn our mercury into hydrogen. And so our final product will end up looking like this. It's going to look the same, except our mercury will be a hydrogen. Okay, yeah, that will be our final molecule. Yeah, yeah, thanks for watching, guys. That's the that's the oxymercuration and demercuration reaction. Thanks.